how silicon carbide ceramics rule the high-end industry. It is not a metal but harder than steel. It was born in the laboratory, but supports the most cutting-edge human science and technology, from the vast space to the chip inside the square inch. A kind of supermaterial called reaction-sintered silicon carbide is quietly changing the world. Today, let's unveil its mystery. Reactive sintering of silicon carbide may sound complicated, but the principle is ingenious. Think of it as an elaborate chemical reaction magic. Craftsmen first press very fine silicon carbide powder and toner into the desired shape, which we call billet. It is then fed into a furnace at temperatures exceeding 1400 C, where it comes into close contact with molten silicon. That's when the miracle happens. Carbon and silicon react violently to create new silicon carbide crystals that hold the original particles together like superglue, while the excess silicon fills in all the tiny pores, resulting in a perfect part that is extremely dense and virtually poreless. This process gives it a superb combination of high hardness, high temperature resistance, corrosion resistance, and excellent thermal conductivity. So how powerful is this combination punch? We let the data speak. Its hardness is as high as 9.5 on the Mohs scale, second only to diamonds. It is also stable in the flames of 1600°. Its thermal conductivity is dozens of times that of ordinary ceramics. Because of this, it has become a top industry. Scramble meat and potatoes. In the semiconductor field, the chip manufacturing process requires an extremely pure and stable environment. The high purity, high thermal conductivity, and high temperature resistance properties of silicon carbide ceramics make it an excellent choice for wafer trays and heat treatment fixtures, ensuring the precise birth of each chip. In aerospace, engine efficiency and heat resistance are central. Silicon carbide components can withstand temperatures of thousands of degrees and enormous stresses here, contributing to increased thrust and efficiency. In the chemical and energy sectors, it is corrosion resistant enough to cope with strong acids and alkalis, and is used to make critical pumps, valves, and seals that last far longer than conventional materials. If traditional manufacturing methods have been amazing, the incorporation of 3D printing technology has completely released the design shackles of silicon carbide. In the past, machining complex-shaped silicon carbide parts was extremely difficult and costly. Now, 3D printing technologies like direct ink writing DIW give us the freedom to draw any complex silicon carbide part like a tube of toothpaste. At the heart of this technology is a special ink made from a precise blend of silicon carbide nano particles and pre-ceramic polymers, which can be extruded smoothly, but also achieves extremely low shrinkage, up to less than 5%, and high strength. After high temperature treatment, this means that we can create hollow porous, one-piece lightweight components that are completely unattainable by conventional methods. From customized semiconductor fixtures to lightweight, heat-resistant components for aerospace vehicles, 3D printing is pushing the boundaries of silicon carbide applications to unprecedented heights. Even in April 2025, China has released a group standard dedicated to 3D printing reaction-sintered silicon carbide, signaling that the technology is maturing and becoming standardized. Changes in the world often begin with an unassuming material. This little piece of ceramic may be behind the next technological advancement. If you found this issue informative, be sure to like, subscribe, and turn on the little bell. Tell us in the comments section what other industries you think silicon carbide will change. We'll see you in the next issue.